In this video, we are going to look at some conceptual questions involving partial derivatives. So our example says, suppose that f of 1 comma 7 equals 8. And suppose also that the partial with respect to x, when x is 1 and y is 7, is equal to negative 2. And the partial with respect to y at that point is equal to 5. Describe what these values mean. Part A asks us to do this graphically, and part B asks us to describe what they mean as rates of change. And later we're going to do a part C, which is going to ask us to estimate the z-coordinate of a point when x is equal to 1 and y is equal to 10. Alright, but let's bring it back here and let's first begin with part A, which asks us to describe what these values mean graphically. And in this question, by the phrasing these values, I'm referring specifically to the partial derivative values. The partial derivatives. So when it says the partial with respect to x equals negative 2, what does that mean graphically? And when it says the partial with respect to y is equal to 5, what does that mean graphically? Okay, so I want to be able to describe what fx means, the partial with respect to x, and what does fy, the partial with respect to y, mean. So for this, let's recall what the picture looks like. So let's say that I have my 3D axes, so x, y, and z, and I draw their negative directions. Okay, and in general, I may have the graph of some surface. So I'm going to begin to draw like sort of one kind of edge of the surface. Maybe it's like curving upwards this way. And I'm going to draw a couple points there. And then from this point at the top, I'm going to start to make it go this way, kind of like back, and a point there. And then from that back point, I'm going to make it come back down, closer to that other bottom corner point. And I'm going to make this other bottom corner point connect with that other corner point. So what this gives us is this kind of like kind of bent, wavy sheet of paper shape. But imagine that this surface extends infinitely. So I've just drawn a part of it, but imagine it does extend infinitely. And we are inputting x is 1 and y is 7 into this function. So let's look at where x is 1 and y is 7. Maybe that's here. So if I draw some dashed lines, so when x is 1, I draw a dashed line. And then when y is 7, I draw a dashed line, this time parallel to the x-axis. And where they meet, we have reached a point where we've gone 1 unit in the x direction and 7 units in the y direction to reach this point right here that I'm shading in blue. And then from that point, I'm going to draw up until I touch the surface. And I won't write this down, but at that point on the surface, the z-coordinate should be 8. Because the problem tells me that f of 1 comma 7 equals 8. So 8 is the z-coordinate at that point on the surface. I want to focus on these partials, and what do they mean graphically? Okay. So if I were to look at this point on the surface that I'm at, where x is 1 and y is 7, and if I were to start to move along the surface, but keep the x value fixed. So if I want to keep the x value fixed at 1, but move along the surface, so that means I'm going to let the y value change, so the y value could get bigger, and maybe as the y value gets bigger, I start to move this way as the y value gets bigger, and maybe as the y value gets smaller, I would move down this way. But overall, I'm keeping the x value fixed. So imagine along that green curve, every single point has an x value 1, but just the y value is changing. And as that happens, the z value will also change depending on where we are on that surface. And one thing that I can do now that I have this curve where x is fixed is at that point, I can draw a tangent line to that green curve. And that tangent line might look something like, maybe something like that. The tangent line just has to be a line that kind of matches how steep that curve is right at that one point. So that purple line that I've drawn is a tangent line. But this is a tangent line purely in the y direction because I'm keeping the x value fixed. And from our knowledge of partial derivatives, we know that when we keep x fixed, that is reminding us of the y partial. So the y partial, fy, is going to represent the slope of that tangent line we just drew. Slope of the tangent line in the y direction. All right. So now instead of keeping x fixed, if I kept the y value fixed, at 7, but let the x value change, then I might get a curve that looks something like, this. Maybe all of the points on this blue curve have this y value of 7, but the x value is changing. Okay, so I get some curve looking like this. Okay, and if I were to draw the tangent line, now in this new direction, this is in the x direction at that point, it's going to be a tangent line to this blue curve I've just drawn. And that tangent line looks like, it might look something like this. Okay, so that orange line is a tangent line in the x direction. So notice that the y value is fixed along that blue curve. And from our knowledge of partial derivatives, the y value being fixed reminds us of x partial derivatives. So the partial of f with respect to x. Graphically, that will represent the slope of the tangent line in the x direction. All right, so in general, this is what partial derivatives, when we have a function of two variables, represent in terms of my graph. Okay, so let's answer specifically in this question what these partial derivatives mean. Okay, so in our specific question, the slope of the tangent line in the x direction, that one was given to be -2, and the slope of the tangent line in the y direction is 5. Those are the values that were given to us in this problem. And overall, all of this is referring to at the point where x is 1, y is 7, and the y value was 8. All right, so now let's interpret, well, what do these mean as rates of change? That's going to be part B. So as rates of change. So let's begin with fx. So for fx, that would be saying if y is fixed, and x increases by 1 unit, f, our function, will, because the slope is negative in the x direction, that means our function, we're going to approximate it is going to be going down. Our function will decrease. Function will decrease by approximately whatever the slope is. It's -2, will decrease by approximately 2 units. And I can see that from the graph. From the graph, it does look like as x gets bigger, so as we move this way from our point up there, it looks like that as we move along this orange tangent line, as x gets bigger, the z values are getting lower. They're getting smaller and smaller. So that's good. We're saying that as x increases by 1 unit, our function will decrease by approximately 2 units. And by f here, I'm talking about the outputs of the function, which are the z values. So we can say something similar for fy. So for fy now, we would say if instead x is fixed and y increases by 1 unit, that means our function's outputs will, notice that the slope in the y direction is 5, so f will now increase. F will now increase by approximately 5 units. Okay, so that's how we interpret what those partial derivatives mean as rates of change. And I can see that from the picture as well. If I look at my picture, in this y direction, if I let y get bigger here, and I move along that purple tangent line in the y direction, as y gets bigger, the z values also get bigger. The z values are also increasing. And that's what my statement under rates of change is saying. So finally, we want to do part C, which asks us to estimate the z-coordinate when x is 1 and y is 10. So it's helpful to remember what it is that we know, the point that we're given information about. I know what's going on if I plug in x is 1 and y is 7 into the function. This outputs 8. And I want to estimate f of 1, 10. When I plug in x is 1 and y is 10 into my function, that'll output the z value. So if I change my input from 1, 7 to 1, 10, we are keeping x fixed. It's staying 1. But y is changing. Y is increasing. Y, let me just say y increases by 3. Okay, so there's 2 ways that I'll talk about to figure out this estimated change now in the z-coordinate. So for my first method, let's focus on, because x is fixed, I know it's going to involve the y partial. So the y partial at this point, 1, 7, where x is 1 and y is 7, is 5. And that means that when x is fixed and y increases by 1 unit, that z also increases by approximately 5 units. Okay, so now we just got to make y increase by more. So thus, if y increases by 3 times as much, if y increases by 3 units, then z increases by approximately, it would be 3 times 5, which is 15 units. Okay, so let's just put this together now. I know how much my z value is increasing by. So if I need to figure out my new z value, I would take the starting z value. The starting z value is 8. And I'm going to add to that how much my z value changed by. We've just said it's going to increase by approximately 15 units. So I'll add 15, which gives me 23. And that's my estimated z-coordinate. That's the estimated z-coordinate when x is 1 and y is 10. Okay, so let's talk about one other way that we could have reasoned that out. Method 2. So with method 2, we're going to use our partial derivative notation. So we are using the partial of our function with respect to the variable y, so del f del y. And a partial derivative, we've talked about what this represents as a rate of change. But a partial derivative is technically what's called an instantaneous rate of change. An instantaneous rate of change is approximately equal to an average rate of change. And the average rate of change is the change in the output over the change in the input. And in this case, when I do the partial with respect to y, what's changing is the y value. So the top is the change in the output of our function. The bottom is the change in the input of our function. But notice the similarity between the two sides and how they are notated. Like I have f's on the top and I have y's on the bottom. Those are matching up. The left-hand side has these del symbols to indicate it's a partial derivative. The right-hand side has these deltas, and that indicates it's an average rate of change. And now let's plug in everything that I know. I know the partial with respect to y is 5. That's going to be approximately equal to the change in f over, I know how much y is changing, because if I look at our points here, the y value is going up by 3. So the change in y is 3. And if I rearrange, whoops, whoa, it totally got shifted there. Whoa, okay, so the denominator should be 3. And if I isolate delta f is approximately equal to 5 times 3, which is 15. And that's the same thing that we got above. We said our z value was increasing by approximately 15 units. So this value tells us that the z coordinate increases, because this is a positive number, increases by approximately 15. If it was a negative value, our z coordinate would be decreasing by approximately whatever the value was. Okay, so we could write down our new z value as we did above. We take our old z value, which is 8, and add how much it's changing. It's increasing by 15, and that gives me 23. And that's our answer.